Hello students, so this is a new problem of the portion hydrodynamics. Look at the question. You're having a tube having two thin vertical tubes also. If this tube had an ideal liquid of density rho and this tube is made to rotate with angular velocity omega about this axis, then we have to find out the two of the thing. Those are asked. One, what is the variation of pressure gradient with the distance? And the distance is to be measured from axis. And if this h is called n times omega square L square upon 2g, what is the numerical value of n? So very interesting question. We are having two vertical tube. The separation between them is L each. So let's discuss and let's find out how to tackle with this question to find out the numerical value of n and the graph of the pressure gradient. Look at this story. When you made this system to rotate, every point which is linearly A or B or C all are at a distance different from the axis. So let's not find out the total effect on the whole system as a single system. Let's find out, let's take a small distance first because every portion is feeling a distance centrifuge. I'm taking a very small length of this liquid horizontally at a distance x from the axis. Look at the forces. Suppose the forces of the liquid on this small portion is F1 and F2. As you know that the system is rotating, that means out of F2 and F1, we need a centripetal force. So we have to start the story like this, F2 minus F1. This is just nothing but a small difference of forces. Because of this rotational system, this is nothing but a net centripetal force called M, R and omega square. Why I'm taking M? You know that this is a small portion of the mass we are taking. And this is the portion which we are taking from here is at a small distance dx. So this is your force, the net force. This is directed towards the center. That will give you the necessary centripetal force. Let's find out the small mass over here. The density of your liquid is stated to be rho. We call it mass upon the volume. Have a look on that. This small portion suppose have the area, cross-sectional area A, and the width is dx. So let's find out this dm, what we call it as rho A dx and x and omega square. This net force acting on this small portion, if you get it divided by A, you will get this one as the system's net pressure difference on both sides. Our first problem is over. If you find out dt by dx, you will get it like this. So what is this? This is nothing but this is actually your pressure gradient. And this pressure gradient is very clearly is directly proportional to the x. So if you're taking the first part, the part is so easy that if you're taking as the pressure gradient, how it is changing with the horizontal distance from the axis, this is a directly proportional phenomenon. Now let's find out the second problem. So the pressure difference is there. We have calculated two of the equation that will give you the pressure difference. Now let us find out the pressure difference so created at these 2 points which are at a distance L and 2L from here. That is between the point P If you want to find out this pressure difference between the point P and Q, let us integrate the concept for finding out the net pressure difference. Taking the limit from L to 2L means taking the pressure at P and pressure at Q. The pressure difference you are getting PQ minus PP is equal to rho omega square, and this is just nothing but x square by 2 with the limit this one. What will we do? Put the limits, calculate the pressure difference PQ and PP, rho omega square. If you put the first limit, you will get 4L square upon 2 minus L square divided by 2. So finally, what pressure difference we are getting between these 2 points? If you can check it, the pressure difference so created between these 2 points is nothing but what the word is. This is 4L square, this is 2L square, sorry, and 1 by 2 minus L square. So what will you get? You will get 3L square by 2. So the net pressure difference you are getting is this one. But have a look on that. If you're looking at these of the 2 vertical capillaries, they're having a pressure height difference of h. So according to the hydrostatic view, the pressure difference according to hydrostatic view between these 2 points has a height difference of h. So what is the pressure difference? Is h rho g. If you put these 2 equations, the third and the fourth, in equal to each other, you will get h rho g is 3 by 2 rho omega square L square, and the rho get cancelled out. Your h is there, you will get 3 omega square L square divided by 2g. So very clear from this. What is the value of that numerical factor n? The problem is over. Thank you, and check this problem. This is a very important problem in the rotational concept of an ideal fluids. Thank you.